I'm David Attenborough, and this is the story of our planet's birth. Not the Earth we know with its blue oceans, green forests, and familiar skies, but a world of fire, of chaos, of unimaginable violence. 4.5 billion years ago, the solar system is young. Where our planet will one day spin, there is only dust. Fragments of rock and metal circling a newborn star. They drift, they collide, they merge. Slowly, the world begins to take shape. It glows with the heat of its own making. Molten rock stretches from horizon to horizon. There is no solid ground, no water, no air we could breathe. The surface burns at temperatures that would melt steel. This is Earth. Our Earth, unrecognizable. And yet within this hellscape, something remarkable is about to unfold. Over the next 500 million years, this molten sphere will cool, oceans will form. And in those dark ancient waters, the first sparks of life will flicker into existence. It is a story written in stone, in crystals older than any mountain, in bands of rust laid down before oxygen filled the sky. In the silent testimony of stromatolites, structures built by creatures so small, they would remain invisible for billions of years. By the end of our journey together, you will understand how a ball of molten rock became a living world, how the moon was born from catastrophe, how water arrived from the depths of space, and how, in the most hostile conditions imaginable, life found a way to begin. If you find wonder in what follows, consider subscribing. It helps us continue bringing these stories to you. But for now, settle in. Let the day's concerns drift away. We're going back to the beginning, to a world of fire. 4.6 billion years ago, in a quiet corner of the Milky Way, a cloud of gas and dust began to collapse. Perhaps a nearby supernova triggered it. Perhaps gravity simply reached a tipping point. Regardless, the collapse had begun. The cloud spun as it contracted, flattening into a disk. At its center, matter compressed until hydrogen atoms fused. Our sun ignited around this newborn star. Dust continued to swirl. Tiny grains collided. Some shattered, others stuck. Pebbles became boulders. Boulders became worlds. One of these growing bodies would become Earth. It had no oceans, no continents. Simply a ball of molten rock, growing larger with every collision. Heat radiated from its surface. The heat of impacts, the heat of radioactive decay. And still the collisions continued. What did this young Earth look like? There was no blue, no green, only the angry glow of molten rock stretching in every direction. A magma ocean hundreds of kilometers deep. The surface temperature exceeded 1200 degrees Celsius. Nothing solid could exist. And yet, order was emerging. Deep within, dense iron and nickel sank toward the center. Lighter silicates rose. Earth was differentiating, organizing into layers. A metallic core, a rocky mantle, the faintest beginnings of a crust. From space, our planet would have appeared as a dim red ember, unremarkable, but destined for something extraordinary. Approximately 50 million years later, disaster struck. Another world, roughly the size of Mars, had been growing nearby. We call it Tania. For millions of years, Earth and Tania danced around each other, their orbits destabilizing. Then they collided. Tania struck at an angle, 15 kilometers per second. Both worlds transformed instantly. Tania's core plunged into Earth and merged with our own. The outer layers vaporized. A vast cloud of molten debris erupted into space. Within a century, this material coalesced into a new sphere. The moon, born from catastrophe, it hung close then, perhaps 20,000 kilometers away. Vast in the sky, raising tides in the magma below. The collision nearly destroyed Earth. Yet without it, our planet might never have become habitable. Scientists call this era the Hadean Aeon, named for Hades, god of the underworld. For 500 million years, Earth remained a hellscape. The crust formed and reformed, constantly shattered by impacts, swallowed by eruptions. Almost no rock survives from the Hadean. Only tiny zircon crystals, 4.4 billion years old, whisper that solid ground ever existed. Asteroids rained down constantly. Each impact remelted the crust. But some carried something precious. Water, locked within their minerals, carbon compounds, the raw ingredients for something remarkable. The Hadean seemed utterly hostile to life. But this world of fire could not last forever. Deep in space, billions of comets were circling. Cold, ancient, heavy with ice. And they were heading our way. The bombardment had not ended, but it was changing. 4 billion years ago, the inner solar system remained a dangerous place. Asteroids and comets, leftovers from planetary formation, still careened through space on chaotic orbits. Earth remained a target. Impact after impact struck the young planet. But these visitors carried gifts. Comets, born in the frozen outer reaches of the solar system, contained water. Not liquid water, ice, locked within rock and dust. When they struck Earth's molten surface, that ice vaporized instantly. Steam erupted into the atmosphere. With each impact, more water accumulated in the thickening air above. Earth was slowly drowning in its own sky. The planet was cooling too. Gradually, the magma ocean that had covered the surface began to solidify. A thin crust formed, dark basalt, riddled with cracks, constantly broken and rehealed. In Australia's Jack Hills, scientists have found tiny zircon crystals dating back 4.4 billion years. These microscopic grains tell us something remarkable. Solid rock existed, even then. More importantly, the chemistry within these zircons suggests they formed in the presence of liquid water. Not steam, liquid. Somehow, even in the Hadean hellscape, water had begun to pool. Imagine that first rainfall. The atmosphere, thick with steam, finally cooled enough for condensation. Droplets formed. They fell toward the surface and vaporized before reaching it. The ground was still too hot, but the rain continued for thousands of years. Millions, perhaps. Slowly the surface cooled further. And then, one day, the rain reached the ground. It pooled in low places, craters, volcanic basins. The water was hot, near boiling and acidic. It would have dissolved flesh in moments, but it was liquid. It stayed. The first oceans were shallow, temporary. Impact still boiled them away periodically. But they reformed, each time larger, each time more persistent. The planet was finding equilibrium. From space, Earth was transforming. The angry red glow faded. Dark patches appeared, cooling crust, and between them something new, blue, faint at first, then spreading. Water reflecting the light of the young sun. Our planet was becoming recognizable. Not hospitable. Not yet, but no longer entirely alien. The oceans grew deeper. The crust grew thicker. The bombardment slowed as the solar system gradually cleared its debris. Earth was settling into something stable. But stability brought new challenges. The young sun was weaker then, 30% dimmer than today. By all calculations, Earth should have frozen solid. The oceans should have become ice. Our planet should have become a permanent snowball, locked in cold forever. And yet, it didn't. Something was keeping Earth warm. Something in the atmosphere, a thick blanket of gases, trapped just enough heat to maintain liquid water. The planet balanced on a knife's edge. But what happened next would change everything. Deep beneath those young oceans, chemistry was stirring, and it was about to come alive. The Hadean had ended. Earth had survived its violent infancy. 4 billion years ago, a new chapter began, the Archean Aeon. The name comes from the Greek word for beginning, and in many ways, this was when Earth truly began. The planet looked nothing like today. The sky was orange, perhaps pale brown, thick with methane, carbon dioxide, and nitrogen. No oxygen. The sun appeared dimmer, smaller, filtered through that alien haze. And the oceans, those precious hard-won oceans, were not blue. They were green, perhaps brown. rich with dissolved iron and other minerals. But they were stable, and that changed everything. Beneath those strange waters, the seafloor was violently active. Volcanic vents punctured the crust, spewing superheated water laden with chemicals. These hydrothermal vents created zones of intense energy, chemical gradients, where different compounds met and reacted. Here, in the darkness, the building blocks of life were assembling. Amino acids, nucleotides, lipids, the fundamental molecules that would one day compose every living thing. They formed spontaneously in this chemical soup, driven by heat and energy from below. We call this abiogenesis, life emerging from non-life. The precise mechanism remains one of science's greatest mysteries. But the evidence points here to these volcanic vents, to this dark, hot, chemically rich water. Meanwhile, above the waves, the first continents were rising. The Archean Earth had no large landmasses. Not yet, but small protocontinents, islands of granite, began to emerge from the basalt seafloor. These cratons, as geologists call them, were the seeds of future continents. The Pilbara Craton in Australia, the Carpovel Craton in South Africa. They survive today, 3.5 billion years old. Walk on them, and you walk on the oldest solid ground on Earth. The planet was restless. Volcanic eruptions occurred constantly. The thin crust recycled itself rapidly. Mountains rose and eroded within millions of years. Nothing was permanent. And yet, amid this chaos, something extraordinary was taking hold. In shallow waters, along coastlines of those early protocontinents, strange structures began to form. Layered domes of sediment, built up over centuries. They were not geological formations. They were built by life. Microbial mats, thin films of primitive bacteria, trapped sediment and minerals as they grew. Layer upon layer accumulated. Over thousands of years, these structures grew into mounds. We call them stromatolites. They are the oldest visible evidence of life on Earth. In Western Australia, at a place called Shark Bay, stromatolites still grow today, living windows into our deepest past. When you look at them, you are seeing the same process that shaped our planet 3.5 billion years ago. Life had arrived, fragile, microscopic, but tenacious. It clung to the margins of a hostile world. It fed on chemicals and dim sunlight. It multiplied, and slowly, invisibly, it began to change the planet around it. The next transformation would take billions of years, but it had already begun. Something was stirring in the chemistry of these microbes, a new way of capturing energy, and it would remake the world. How does chemistry become biology? This question haunts scientists to this day. We know that life emerged on Earth. We see its descendants everywhere, in every ocean, every forest, every handful of soil. But the precise moment when molecules became alive remains hidden. What we do know is this. Somewhere around 3.8 billion years ago, something extraordinary happened. The ingredients were present: amino acids, the building blocks of proteins; nucleotides, the components of genetic material; lipids, fatty molecules that form membranes. All of these existed in Earth's early oceans, formed by chemical reactions at hydrothermal vents, delivered by comets, created by lightning strikes in the atmosphere. But ingredients alone do not make life. The key was organization. Somehow, these molecules began to work together. Lipids formed tiny spheres, primitive membranes that separated inside from outside. Within these bubbles, chemical reactions could concentrate, complexity could build. Scientists call this the RNA world hypothesis. Before DNA, before proteins, there may have been RNA, a molecule that can both store information and catalyze chemical reactions. In the warm, chemical-rich waters of early Earth, RNA molecules may have begun copying themselves, imperfectly at first. Errors crept in, variations arose, and with variation came selection. Some RNA molecules copied themselves faster. Some were more stable. Over millions of years, these successful molecules outcompeted others. Chemistry had become something new. It had become evolution. The first true cells appeared around 3.5 billion years ago. We call them prokaryotes, simple cells without a nucleus, just a membrane, some genetic material, and the machinery to reproduce. Unimaginably primitive by today's standards, but they were alive. These early microbes were not passive. They consumed chemicals from their environment. They grew, they divided, they spread. Two great domains emerged, bacteria and archaea, each adapting to different conditions. Some thrived in volcanic hot springs. Others colonized the open ocean. Some lived in complete darkness, feeding on chemical energy. Others evolved something revolutionary, photosynthesis. The earliest photosynthesis was not like today's. These primitive microbes captured sunlight and used it to build organic molecules, but they did not produce oxygen. They used hydrogen sulfide, or iron, or other chemicals as raw materials. An oxygenic photosynthesis, we call it. It was enough to fuel an explosion of life. Microbial mates spread across shallow seafloors. Stromatolites grew in their billions. The oceans teemed with invisible life, countless cells, consuming, growing, dividing. Earth had become a living planet, and yet most of this life remained hidden. The surface waters hosted photosyntheses, but beneath them, in the darkness of the deep ocean, another world existed. A world independent of sunlight, a world powered by Earth's internal heat. This hidden biosphere may have been larger than anything on the surface, and it held secrets that would only be discovered billions of years later. What lay in those depths? What strange forms of life thrived in eternal darkness? The answers would reshape our understanding of life itself. Sunlight penetrates only the upper layers of the ocean. Below 200 meters, darkness begins. Below 1,000 meters, it is absolute. No light has ever reached these depths. And yet, life thrives here. 3.5 billion years ago, the deep ocean was not empty. Far from it. While stromatolites grew in sunlit shallows, an entirely different ecosystem flourished below. One that needed no light at all. Hydrothermal vents punctured the seafloor. Cracks in Earth's crust where seawater met magma. Water superheated to 400 degrees Celsius erupted from these chimneys, yet remained liquid under the crushing pressure. Black smokers, we call them, for the dark, mineral-rich plumes they release. Around these vents, chemistry ran wild. Hydrogen sulfide, methane, ammonia, iron, manganese, a toxic brew by our standards. But to early microbes, this was paradise. The chemical gradients between hot vent water and cold seawater provided energy, lots of it. Chemosynthesis, life powered by chemistry, not light, dominated here. Archaea clustered around the vents. Some thrived at temperatures that would kill any modern animal. Thermophiles, we call them, heat lovers. Others fed on methane seeping from the seafloor, methanotrous. Others still consumed hydrogen directly, exhaling methane as waste. These were not marginal creatures. They may have been the majority of life on Earth. The deep biosphere extended beyond the vents themselves. Microbes colonized the rocks below the seafloor. They lived in cracks and pores, feeding on chemicals seeping through the crust. Some scientists estimate that even today, the subsurface biosphere rivals the mass of all surface life combined. In the Archean, it may have been even larger. This hidden world operated by different rules. No seasons, no day or night, no weather. Just constant chemical energy available for billions of years. Life here was slow. Metabolisms operated at a fraction of surface rates. But time was abundant. And something else was happening in these depths. The iron oceans of the Archean contained vast quantities of dissolved metal. The water itself was green with it. When microbes died, their remains drifted downward. Iron bonded with organic matter, layers accumulated on the seafloor. We see these layers today, banded iron formations, alternating stripes of iron-rich and iron-poor rock. They stretch for hundreds of kilometers in ancient cratons. The Hamersley Basin in Australia, the Mesoba Range in Minnesota. Silent testimony to those ancient iron seas. But the iron would not remain dissolved forever. Something was coming. A transformation so profound it would poison most life on Earth. A catastrophe triggered not by asteroids or volcanoes, but by life itself. Somewhere in the sunlit shallows, a new kind of microbe was evolving. One that would split water molecules and release a deadly gas, oxygen. The world was about to change, and nothing would survive unchanged. For over 1 billion years, life had flourished without oxygen. The atmosphere contained none, the oceans contained none, and life preferred it that way. Oxygen is dangerous. It reacts with almost everything. It tears apart organic molecules. It corrodes metal to the anaerobic microbes that dominated early Earth. Oxygen was poison, pure and simple. But evolution does not care about consequences. Around 2.7 billion years ago, a new type of microbe appeared. Cyanobacteria, blue-green algae, though they are not truly algae at all. These remarkable organisms evolved a new form of photosynthesis, one that used water as a raw material. The chemistry was elegant. Cyanobacteria captured sunlight. They split water molecules into hydrogen and oxygen. The hydrogen combined with carbon dioxide to build sugars. Energy storage. The oxygen was waste, released into the water. At first, nothing happened. The oceans absorbed this oxygen effortlessly. Dissolved iron, billions of tons of it, reacted with the oxygen immediately. Iron oxide formed. Rust, essentially. It precipitated out of the water and sank to the seafloor. Layer after layer, year after year. Century after century. The banded iron formations we see today record this process. Each band represents millions of years, iron capturing oxygen. The oceans rusting from within, but the cyanobacteria kept multiplying. Stromatolites spread across every shallow sea. Mats of cyanobacteria covered coastlines worldwide. Each cell tiny, each cell producing oxygen. Trillions upon trillions of them. Eventually, the iron ran out. Around 2.4 billion years ago, the oceans could absorb no more. Oxygen began escaping into the atmosphere for the first time in Earth's history. Free oxygen accumulated in the air. We call this the Great Oxygenation Event. Scientists also call it the oxygen catastrophe, because for most life on Earth, it was exactly that. Anaerobic organisms, the bacteria and archaea that had thrived for over 1 billion years, found themselves poisoned. Oxygen infiltrated their environments. It destroyed their enzymes. It disrupted their metabolism. Mass extinction followed. We have no fossils to count the dead. But the toll was almost certainly enormous. Perhaps the greatest extinction in Earth's history. Caused not by asteroids, not by volcanoes, by life itself. The survivors retreated. They found refuge in oxygen-free zones, deep sediments, stagnant waters, the guts of other organisms. Their descendants remain there today, hidden from the toxic air. Meanwhile, the world transformed. The sky changed color. Methane, which had helped warm the planet, reacted with oxygen and vanished. The greenhouse weakened. Temperatures began to fall. Earth was heading toward a crisis. The oxygen that cyanobacteria had released, the waste product of their success, was about to trigger something unprecedented. A cold so severe it would encase the entire planet. Ice was coming, and it would nearly end everything. The warmth was fading. For billions of years, Earth had maintained liquid oceans despite a dimmer sun. Methane in the atmosphere produced by countless microbes had trapped heat like a blanket. a delicate balance. A fragile warmth. Oxygen destroyed that balance. As oxygen accumulated, it reacted with atmospheric methane. The methane vanished. The greenhouse effect weakened, and temperatures began to drop. At first, the cooling was gradual. Ice formed at the poles. Glaciers crept down from high mountains. Nothing unprecedented. Earth had experienced cold periods before, but this was different. Around 2.4 billion years ago, the cooling accelerated. Ice sheets advanced from the poles toward the equator. Snow fell in regions that had never known frost. The white surface reflected sunlight back into space, cooling the planet further. A feedback loop had begun. Ice begets ice. Scientists call this the Huronian glaciation, named for rocks near Lake Huron in Canada, where evidence of this ancient ice was first discovered. It was not one event but a series of glacial advances and retreats spanning 300 million years. The longest winter in Earth's history. At its peak, ice may have reached the equator. Some scientists believe Earth became a snowball, completely encased in ice, kilometers thick. Others argue that open water survived near volcanic islands or in thin patches along the equator. Either way, life faced its greatest challenge. The stromatolites that had transformed the atmosphere now struggled to survive. Photosynthesis requires sunlight. Under thick ice, little light penetrates. The cyanobacteria that had conquered the world found themselves imprisoned. But life did not surrender. Near volcanic vents, hot water kept ice at bay. Small refugia, pockets of survivable habitat, persisted even in the frozen world. Deep beneath the ice, hydrothermal ecosystems continued as they always had. The chemosynthetic microbes of the abyss barely noticed the catastrophe above. Life endured, diminished, but present, and Earth itself would provide rescue. Volcanoes continued erupting throughout the glaciation. They released carbon dioxide, a greenhouse gas, into the atmosphere. Normally, weathering of rocks removes carbon dioxide from the air, but weathering requires liquid water. Under ice, weathering stops, carbon dioxide accumulated. Slowly, over millions of years. Eventually, enough accumulated to trigger warming. The ice began to melt, slowly at first, then rapidly. The feedback loop reversed. Dark water absorbed sunlight, temperatures rose further, ice retreated toward the poles. Earth emerged from its frozen prison. The world that thawed was not the same world that had frozen. Oxygen remained in the atmosphere. The anaerobic paradise was gone forever. But new possibilities had opened. In the meltwaters of a recovering planet, life would find new paths forward. The stage was set for the next 3 billion years, and eventually for us, 500 million years had passed since Earth's formation. 500 million years of fire, bombardment, cooling, and transformation. The planet that emerged from the Huronian ice was unrecognizable from the molten sphere that had begun this journey. And yet, the evidence remains. In Western Australia, in the ancient Pilbara Craton, rocks 3.5 billion years old still bear the marks of those earliest times. Stromatolites frozen in stone, the layered domes built by microbes that changed the world. Run your hand across their surface, and you touch the work of life itself. Remarkable. In South Africa, the Kapvale Craton preserves similar treasures. Ancient greenstone belts, volcanic rocks from the Archean seafloor tell of a world in constant motion. Hydrothermal vents, undersea eruptions, the restless churning of a young planet. The banded iron formations speak loudest of all. In Australia's Hamersley Basin, in Brazil's Carajás region, in Minnesota's Mesabi Range, these striped rocks stretch for hundreds of kilometers. Each band records a moment in Earth's oxygen revolution. Iron capturing oxygen, rust raining to the seafloor, a planet slowly, invisibly transforming. We mine these formations today. The iron in bridges, in buildings, in automobiles, much of it was laid down by cyanobacteria billions of years ago. We build our civilization on their legacy. And then there are the zircons, tiny crystals, smaller than a grain of sand. Yet within them, atoms preserve records of unimaginable antiquity. Zircons from Jack Hills in Australia date back 4.4 billion years. They formed when Earth was barely 100 million years old. Within their crystal structure, oxygen isotopes whisper of liquid water. Even then, even in the Hadean, these fragments are Earth's oldest memories. Scientists have learned to read them, to extract stories from stone. Isotope ratios reveal ancient temperatures. Mineral compositions indicate atmospheric chemistry. The rocks remember what no living thing witnessed. What have we learned from 500 million years? We have learned that our planet is resilient. It survived the collision that formed the moon. It survived the late heavy bombardment. It survived the oxygen catastrophe and the Huronian ice. Each crisis reshaped the world. None destroyed it. We have learned that life is tenacious. It arose in conditions we would consider hellish. It adapted. It transformed. It remade the planet in its own image. The oxygen we breathe is biological waste, the exhaust of organisms that lived billions of years before us. We have learned that time is patient, 500 million years. It sounds impossibly long, and yet it was only the beginning. Another 4 billion years would follow. Continents would assemble and break apart. Complex life would arise. Fish would crawl onto land. Dinosaurs would rule and vanish. Mammals would inherit the earth. And one species, curious, restless, wondering, would look back at the rocks and ask how it all began. The story continues. It always does. Our planet spins on. The sun rises and sets. Somewhere stromatolites still grow in shallow waters. Somewhere hydrothermal vents still feed creatures in eternal darkness. The processes that shaped those first 500 million years have never stopped. They are happening now, and they will continue long after we are gone. Sleep well, dream of deep time. And remember, you are made of stars, of ancient oceans, of the breath of cyanobacteria. You are Earth's legacy, living stone,